That's okay. You can switch the order. Go ahead.
Thank you for the introduction. And hello, everyone. I'll be presenting our work, Essay to Equivariant, Pushing Dynamics Models for Tabletop Object Manipulation. I'm Seung-Young Kim, and this is joint work with Byung-Do Lim, Yong-Hyun Lee, and Frank Park. Although we may not realize it, we use pushing manipulation in our everyday lives all the time, as this video of a human grasping object shows. Pushing manipulation is also an important skill for a robot, especially for scenarios like the following, in which the robot must extract and grasp an object that is surrounded by other objects. The classical model-based methods of solution would be to identify and locate the objects and use our knowledge of physics or mechanics to push the objects so that they can be manipulated. The problem with this approach is that the shape and mass inertial properties of the object, as well as friction coefficients, may not be known in advance. And in some cases, real-time motion planning may be difficult due to the heavy computation of physics-based models. To address these shortcomings of classical model-based methods, several data-driven methods have been recently proposed. These methods take as input a visual scene ST involving multiple objects, together with a user-provided robot pushing action AT. The output is then the next scene ST+1 of the object after they have been pushed by the robot. Recent methods differ in the choice of visual input and deep neural network architecture. Compared to classical model-based methods, all these methods have the advantage of fast inference and do not require prior knowledge of the object and the environment. However, after we carefully compared the performance of these and other data-driven methods, we found that their generalization performance to be less than satisfying, and they require large amounts of training data. One way to reduce the amount of the training data is to use a network that is equivariant. We now explain what this concept means. Consider the following scene in which a single object on a table is pushed as shown. If the same object is now displaced to another location on the table and the same relative pushing action is applied, then the resulting displacement of the object should just be a displaced version of the original object motion. It should not be necessary to provide this type of redundant training data into the network. A network that possesses this property is said to be equivariant with respect to translations and rotations on the plane. Or more technically, equivariant with respect to special Euclidean group SE2 of planar rigid body motion. The main contribution of our work is a data-driven model for pushing dynamics that is SE2 equivariant. We now describe our SE2 equivariant network architecture. Here is a scene with a table and tabletop object. We first assume that the table surface is flat and orthogonal to the gravity direction and has uniform friction over the table. And for training phase, assume an object placed on a tabletop, and we know the information of the objects, including each object pose Ti and shape parameter Qi in large Q. Also, we consider a following discrete time pushing dynamics model F to predict the motion of the object 1. The model inputs the target object T1 and Q1, surrounding objects from T to Q2, from T and Qn, and pushing action AT. Then it outputs the displaced pose of the object 1, T1 over T+1. Using the same model F, we can also predict the displacement of the other objects as follows. Assume that the object and the pushing action is transformed by the same SE2 transformation C, then these variables look like this. Then the model is desired that its output should be also transformed by the same SE2 transformation C. In this term, we can define that pushing dynamics model F is SE2 equivariant if the following equations hold for all SE2 transformation C. In the test or inference phase, based on this definition, we first recognize the object poses Ti and shape parameters Qi from visual observation. The learned pushing dynamics model, F, then takes the shape and pose information of each scene and each object together with the pushing action and outputs the object displacement. The detailed architecture is as shown. Briefly, let object I with the green color be the object of interest. We first project the SE3 frame Ti to our SE2 frame Ci, which is restricted to lie on the tabletop. We note that the objects can be tilted in this formulation. And all objects together with the pushing action are then transformed by Ci inverse. These values are then passed through several MLP layers, producing the output transformation delta Ti. Finally, the next pose is calculated by multiplying the original pose Ti by delta Ti. This alpha value is SE2 equivariant. For evaluating the proposed dynamics model, we build a pushing manipulation data set in simulation. We use cylinder and cube-shaped objects and of various size as shown in right, and each scene contains up to 4 objects. Examining our results, we see that our method outperforms other methods for the unseen test data set. Although our method requires additional intermediate computations, it shows the best generalization performance using less training data. Shown here are qualitative results of predicting object motions after a pushing action is applied. Our model successfully predicts even complex interactive behaviors of the objects in the test dataset. We also confirm that the proposed model can be used for various downstream pushing manipulation tasks, including moving tasks that moves the objects to their desired poses, and singulation tasks that separates the objects by more than a certain distance tau. Moreover, our model can be directly used for assisting grasping tasks since our methods also estimate 3D shapes of the objects. We can generate candidate grasp poses for the recognized 3D target object as shown in the figure. Then, by checking collisions of the predefined grasp poses with the environment and the other recognized objects, we can define an appropriate reward function which has value 1 if at least one valid grasp pose exists and 0 otherwise. We execute action sequences that maximize the grasp reward function. Notably, without using any ad hoc objective functions, the robot realizes how to reconfigure the object so that feasible grasp poses for the target object can be found. The robot pushes the surrounding objects as the left and flat and large object to the edge of the table as the right. So here is a dirty rendering list. First, currently, it is not trivial to apply it directly to more complex and non-convex shapes. Especially defining shape parameter is not a trivial problem. Second, there could be some situations where the SE2 equivariance does not apply. In this case, our approach can be detrimental. Finally, different mass distributions will lead to different motions, especially when the objects interact with each other. In this case, the dynamics prediction task using only vision data becomes challenging. So finally, here is a summary. In summary, we have proposed a SE2 equivariant pushing dynamics model, and we confirm that our method significantly outperforms the existing visual pushing dynamics models. And finally, we have verified that our method can be used for various pushing manipulation tasks, especially for assisting the grasping tasks. So there are many more interesting topics discussed in our paper, and we invite you to take a closer look. Thank you for listening.